In this problem, I'll talk about the billiard ball's collision at an angle. It's not a head-on collision, but rather it is a collision at an angle. So we have one billiard balls which is moving with a velocity of 5 meters per second, and then an identical ball is sitting here at rest. When the ball hits the second ball at an angle, then after the collision, the first ball starts moving at an angle of 40 degree with respect to its original direction, and the second ball, which was at rest, starts moving in the other direction. And now we have to find out what are the speed of the balls. It should be speeds here. So what are the speeds of the ball after the collision? Okay, so we now have to find out v1f and v2f. Again, v1I means the velocity of the first ball, and I stands for the initial velocity or before collision. And the second ball, as it is sitting rest, this velocity is 0 meter per second. And the v1I means the velocity of the first ball, and the f stands for after collision or the final velocity. So we have given this angle as 40 degree, and I would like you to keep in mind that when the two identical balls, or just like a pool, when you play a pool, when the two balls hit each other at an angle, then after the collision, the angle of separation is 90 degree. So this angle is always 90 degree, and there are two conditions. The one is elastic collision, and the second condition is the mass of the two balls should be exactly equal. If it is, then the angle of separation is always 90 degree. Just keep this one in mind. So if this angle is 40 degree, you know what this angle has to be now. What is it? 50 degree. So this angle is 50 degree. And remember, so in order for this angle to be 90 degree, the mass of the two balls has to be equal, and this has to be elastic collision. Okay, so we already have calculated this one to be 50 degree. And now let's use the conservation of momentum, and we have to write down the conservation of momentum along two axes. First along the x-axis, and then we will write down the conservation of momentum along the y-axis. It doesn't matter what kind of collision is this, the momentum along x-axis and along y-axis is always conserved. Okay, so let's start with the x-axis. So the initial momentum before collision, I'll just write it down. The total momentum before collision it has to be equal to total momentum after collision. Okay, so now let's calculate the total momentum before collision. So this mass is moving along the x-axis. So what is the momentum? The mass time velocity, which is mv1I. This has to be x here, sorry. This has to be I. Okay, so mv1I. And now what is the momentum of the second ball here? The momentum of this ball is 0. Why? Because it is sitting stationary, it is at rest. And now we'll calculate the after collision. So after collision, this ball is exactly not moving along the x-axis, but rather at an angle. Okay. This has to be, again, let me make one v1f cosine theta. So this ball, as I mentioned, it is moving at an angle. So a component of this ball along the x-axis, or the velocity of this ball along the x-axis, is v1f cosine theta. Okay, and the component of this ball along y-axis will be v1f sine theta. Always remember, if this is the angle, this has to be the cosine, and this will be the sine component, the v1f cosine theta. And similarly, we're going to resolve this one into two components, one along the x-axis and another along the y-axis. As this angle is alpha, so the velocity, the component of velocity component along x-axis will be v2f cosine alpha. Why cosine alpha? Because this is the angle alpha. And this component will be v2f sine alpha. If you just can draw this free body diagram, or the direction of the velocity along x-axis and y-axis, then you're good. Then it is pretty simple things to do. All you have to do is resolve this velocity into two components. This component will be cosine component and this will be the sine component. Similarly, resolve this one into two components, one along the x-axis and another along the y-axis. This component will be cosine and this component will be sine. This is. Okay, so now let's calculate all the momentum after the collision. So after the collision, the momentum will be v1f cosine theta. So this is m v1f cosine theta, and the momentum of the second ball will be m v2f cosine alpha, because we have two velocities along the x direction now. The one is coming from this ball and the other is coming from this ball. The first ball and the second ball together now. And as these are the equal masses, this mass cancels out. Okay, so v1f cosine theta is given, which is 40 degree. v2f cosine alpha we already have calculated, this is 50 degree. So just plugging the value of cosine 40 degree, which is 0.77, and cosine 50 degree is 0.64. So this is the total momentum along the x-axis. The same thing we were going to do, the total momentum after the total momentum along y-axis. So the initial total momentum, what is the momentum of this ball along y-axis? It is 0, because this ball is moving along the x direction. And if it, or in other words, if you take the component along y-axis, this angle is 90 degree. So cosine 90 degree will be 0. So this ball doesn't have any component along y-axis. Similarly, the momentum of this ball along y-axis is 0. So the total momentum, initial momentum along x-axis is exactly equal to 0. This is before collision. And now let's take a look after collision. After collision, the first ball has a component of the v1f sine theta, and this one here has v2f sine alpha. So the component of the first ball, or the momentum of the first ball, will be mass times this velocity. That's what I've done here, mass times v1f sine theta, and the mass v2f sine alpha, and the negative sign here because this one has the component in the opposite direction. That's the negative sign. So now we're going to simplify this one. M is the negative sign here and this is 0, so I'm taking this one to the other side. M v1f sine theta, then we'll have m v2f sine alpha. Mass cancels out, and then if you solve for v1f, what you get is V1F is now equal to V2F 1.19. So there is a relation now between the V1F and V2F. So what I'm going to do now, I'll plug this V1F into this equation. Okay, so let's do that now. So I'm just plugging. You see now here 5, we have 5, this is 5 here, and instead of V1F I'm using V2F 1.19, V2F 1.19, 0.77, V2F 0.64, and then solve it. After solving, what you get is 3.21 meter per second. That's the velocity of this second ball. Once we know the V2F, then we can plug this back into this equation and solve for V1F. And we solve for V1F, which is 3.82 meter per second. So that's how we calculate the speed of the ball after collision. So just by using the conservation of momentum, we were able to solve the collision of the balls after the collision. Okay, so this is it for the billiard balls collision at an angle. Again, if you have any questions, any suggestions, any comments, please write down your comment, suggestion, or anything in the comment section below. And at the end, do not forget to subscribe the channel. Thank you.